On January 23, 1960, a small pressure sphere began descending beneath the Pacific. Inside Trieste, Jacques Piccard and Walsh entered water no humans had reached. Their destination was Challenger Deep in the Mariana Trench. Above them, daylight narrowed and vanished as the ocean closed overhead. Below them waited the accepted deepest region on Earth's seafloor. The dive joined engineering risk with a basic geographical question. Could a crewed vessel survive pressure near 11 kilometers down? The descent offered no rescue route and little room for correction. Fuel, gasoline, ballast, and patience formed their path into darkness. Every meter increased the load pressing against the occupied sphere. If you imagine a submarine cabin, Trieste was far more austere. Two men occupied a compact sphere suspended beneath a huge float. Their windows offered tiny circles of darkness and occasional living movement. The opening mystery was whether the craft, crew, and plan would endure. History would depend on physical evidence carried safely back upward. Trieste was a bathyscaphe designed to descend independently from surface cables. Swiss physicist Auguste Piccard developed the bathyscaphe concept for deep exploration. Jacques Piccard continued that work and participated directly in Trieste's development. The United States Navy acquired Trieste and prepared it for deeper operations. Its large float contained gasoline, which is lighter than seawater and nearly incompressible. Iron shot served as releasable ballast during descent and ascent. Electromagnets held the shot, allowing release if electrical power failed. The crew occupied a thick-walled steel sphere attached beneath the float. That arrangement placed human life inside the strongest protected volume. Pressure outside Challenger Deep exceeds 1,000 times sea-level atmospheric pressure. At such pressure, a small structural flaw can become catastrophic. Engineers tested materials and systems, but the full environment awaited below. The expedition operated near Guam aboard naval support arrangements. Walsh, a United States Navy lieutenant, joined Jacques Piccard for the attempt. Their mission followed uncrewed soundings that had identified the deep basin. Those measurements guided the target, but could not guarantee a level landing. Trieste descended by taking on weight relative to the surrounding water. Its crew monitored instruments, communicated intermittently, and watched through viewports. Cold penetrated the cabin as the descent continued for hours. Bioluminescent organisms sometimes marked the otherwise black water outside. Such sightings confirmed nearby life, but did not map the broader community. The verified achievement depended on depth measurement, timing, navigation, and safe return. Partway down, a sharp sound broke the long mechanical routine. Crew later understood that an outer plexiglass window component had cracked. The pressure sphere remained intact, so the descent continued. That decision reflected their assessment inside the craft, not proof of zero danger. You can hear courage in the story, but engineering margins carried them. The bathyscaphe moved through layers of increasing pressure and near-freezing temperature. Navigation at depth was difficult. With limited knowledge of precise horizontal position, sediment appeared when Trieste finally approached the trench floor. The craft settled at Challenger Deep after descending for nearly 5 hours. Piccard and Walsh reported a soft, pale bottom outside their viewport. Their landings stirred sediment that reduced visibility around the vessel. They remained on the bottom for roughly 20 minutes. The brief stay constrained what could be observed or recorded directly. They reported seeing a flatfish-like animal, a claim later questioned scientifically. Hadal fishes are not confirmed at Challenger Deep's greatest depths. The sighting may have involved another organism or a mistaken interpretation. It should not be treated as proof of a flatfish at the bottom. This limitation matters because landmark journeys can magnify uncertain observations. The landing itself is supported by the mission record and successful return. The biological identification remains separate and substantially less secure. To ascend, the crew released iron ballast from the bathyscaphe. Buoyancy then carried Trieste upward, without a conventional propulsion system. The ascent took several hours through the same immense water column. Communication improved as the vehicle neared its waiting support team. The sphere emerged intact, proving humans could survive the deepest known ocean. The achievement was technological, geographical, and psychological rather than a comprehensive survey. Trieste transformed Challenger Deep from a remote sounding into a visited place. Its success established design principles for later full ocean-depth vehicles. Pressure resistance begins with geometry because spheres distribute external loads efficiently. Redundant ballast release provides a passive route back toward the surface. When power fails, released weight can still allow positive buoyancy. This cue-action consequence chain turns failure planning into survival. Modern submersibles use different materials, electronics, and propulsion systems. They still confront the same pressure, darkness, cold, and isolation. Later crewed descents returned with improved cameras, sensors, and navigation. Their observations expanded knowledge without diminishing Trieste's first achievement. If you stood conceptually beside the sphere, its smallness would dominate. The human space was tiny compared with the ocean pressing around it. The mission also showed how exploration can exceed immediate scientific sampling. Its direct data set was limited, but its engineering demonstration opened future access. Access enables repeated measurements, and repetition separates pattern from singular encounter. Dive-inspired deep submergence programs serving geology, biology, and recovery operations. It also revealed how easily a famous observation can outlive its uncertainty. Responsible history preserves both the accomplishment and the unresolved fish identification. The human stakes remain clearest in the vehicle's carefully designed ascent system. Survival depended on releasing ballast after reaching a place with no practical rescue. Future evidence can refine the route, landing position, and environmental conditions. Archived logs, engineering records, and original imagery remain important primary material. Modern bathymetric maps can place the historical dive within improved seafloor terrain. They cannot recreate every movement of a vehicle navigated with older instruments. New descents can compare sediments and organisms across Challenger Deep's separate basins. Long-duration landers can observe changes impossible during a 20-minute visit. Pressure-retaining samplers can preserve biological conditions during recovery. You should still separate those later findings from what Trieste actually witnessed. The 1960 dive answered survivability more decisively than ecology. It proved a crude pressure sphere could reach the deepest accepted seafloor. It did not prove the trench was uniform, empty, or fully understood. Returning to the opening descent, the darkness remains physically unchanged. What changed was humanity's demonstrated ability to enter and leave it. The cracked outer component reminds us that success did not erase risk. The disputed animal reminds us that eyewitness testimony has scientific limits. The safe ascent remains as important as the record-setting arrival. Trieste's first journey to Challenger Deep stands verified, while the world glimpsed through its viewport remains only partly known.